Alrighty, guys. Let's get started. Today we're just going to do a quick exam review session. Figured I would just go over a little bit of the subject matter that's on the exam and just leave everything open for you guys to ask questions if there's certain spots that you want a little more clarification on, a little more help with. Just shout out and let me know, and we can go over it as a class. So the first part of the exam is going to be obviously earth materials. So obviously understand the parts of an atom: protons, neutrons, and electrons, their charges, how they affect the atomic number, the atomic weight, how if you switch from neutrons to protons, how that affects the atomic element itself, and how we use them in radiometric dating to figure out how old rocks are. 3 different rock types. How are they classified? Your igneous, your sedimentary, your metamorphic. For igneous, you have your felsic to ultramafic rocks. For sedimentary, you're designating by grain size. Metamorphic, it's more along the lines of the grade of metamorphism, how long it's been metamorphosed, how much time and pressure has formed it. So that's pretty much it for these. Where do they most likely occur is pretty common too. So let's say we have a divergent plate boundary. What kind of rock are we going to get there? Most likely we're going to get those ultramafic rocks, the basalts, and those are obviously igneous because they're forming from the center of the earth from cooling magma. So keep those things in mind for earth materials. Geologic time, relative dating. How do we know what's older and what's younger? Not exact dating, but just knowing how we can map out older things and younger things and which came first, the chicken or the egg kind of deal. Your basic principles of geology. Make sure you know what each of these mean and how they're important. Principle of superposition, the big one, or original horizontality, lateral continuity, cross-cutting. Those are going to be really important on the exam as well. Radiometric dating, what does it mean to have a half-life of something? And how do we use that to calculate the relative to exact age of a rock? So if we have, if we're looking at carbon-14, which has a half-life of 5,700 years, and it's decayed into half of the atoms are carbon-14, half of the atoms are nitrogen. How old is that rock? That's 1 half-life since it's only decayed by half. So that's 5,700 years old for that rock. And then for your geologic time scale, you don't need to have that memorized, but you need to have an idea of which ones are larger, which ones are smaller. Have an idea of where we are in this time period, and have an idea of what eon, era, period, and epoch we are in right now. That would be important. I'm not going to make you memorize the entire geologic time scale. If you switch majors, then yeah, I'll make you do that. But most of you probably aren't going to switch majors. Plate tectonics is going to be big. So remember, we talked a lot about plate boundaries. We have convergence, divergent, transform, convergence, they're coming together. Divergent, they're splitting apart. Transform, they're sliding past each other. Convergent boundaries, we have a bunch of different types of convergent boundaries. Continental, best example is India and Asia, creating the Himalayas. You get continental rocks, they're lighter, they're less dense, they build up and up. You don't get a lot of subduction there, so you just keep building higher and higher, and that's why the Himalayas are the highest mountains in the world. Continental oceanic is much denser, has a lot more magnesium in it, so it tends to sink and subduct below the continental crust. As that oceanic crust is subducting below the continental crust, it's going to melt. It's going to release all of those, all that moisture in it, the water vapor. It's going to destabilize the rock, melt on its way up, and that's why we get volcanic arcs, island arcs, volcanic arcs. The Andes are a great example. The Cascades, another one. Oceanic is going to give us our island arcs like Indonesia, Philippines, just because everything's so dense. So your volcanic arcs just poke up over the ocean surface as islands. And how are they different? Mainly their density, also the ways that they interact with each other. So keep that in mind. One important thing is going to be hotspots and plate motion. So if we have a hotspot like we do in Hawaii, and we have those island chains, and we know how old each of those islands are, how do we determine the direction of plate motion based on that? Wadati-Benioff zones, remember those graphs showing the locations of these large-scale earthquakes? What is that indicative of? It's indicative of subduction zones. It can tell us a lot about what the subducting plate is doing, the direction it's going, if it's going to keep building up, or if it's going to keep diving down into deeper into the mantle. What happens at mid-ocean ridges and other divergent boundaries? We don't just have rifting along the whole boundary. Because it's tensional and that stress is tensional and it's pulling apart, we're going to get some faulting as well. So think of that plate tectonic map that we had where you saw those transform faults along the mid-ocean ridge. It wasn't just a long divergent boundary, it was broken up into a lot of little segments that were basically 90-degree angles of these faults. And then obviously, what's the lithosphere? What's the asthenosphere? Why is one on top of the other? What are the characteristics of the two of them? And then lastly, earthquakes. Talk about each of your seismic waves, your body waves, primary and secondary waves, your surface waves, the most damaging, Love and Rayleigh waves. How do they move? What direction do they move? Which ones are the fastest? Which ones are the slowest? Stress versus strain is going to be important. Just knowing which is stress and which is strain and how they interact with each other. Remember, as stress increases, strain increases, and you build up strain until you reach the breaking point of whatever material you're enacting that stress upon. If it's a rock, if it's a plate, if it's just a joint system in a rock formation, everything has a certain breaking point that once you get past that point, that's where you get a snap, breaking along the fracture. Calculating recurrence intervals, we've done that a couple of times, so you guys should be good on that. Just remember the basic equation is a period of time over the number of events minus 1, or time period over the number of intervals. Remember, if we have, think of your hand, if you have 5 events and you only care about the space in between the events, just the space in between your fingers. 1, 2, 3, 4. So think of it that way. Fault systems. Which one is the hanging wall? Which one is the footwall? Remember, the footwall is the one on the bottom, the one you can walk on. That's why it's the footwall. The hanging wall is the one with the steep angle where if it was by itself, you would have to rock climb on. That's the hanging wall. If we're looking at a fault on the surface, is it left lateral? Is it right lateral? Meaning which direction did the other side go? So keep that in mind. If we have a fault system and then we get erosion, do we have older rocks on top? Do we have younger rocks on top? And how is that going to affect our perception of the age of the rocks and the difference in the age of the rocks? And then what's a normal fault? What's a strike slip fault? What's a thrust fault? Basically, that's your direction of motion. Normal, you're pulling apart. That's your tensional stress. Strike slip, you're sliding past each other. Thrust fault, that's your compression. You're pushing the hanging wall up. And obviously magnitude and intensity, there's a difference between the two. How are they used? Because they're not interchangeable terms. How do we calculate differences in magnitude? If we have a magnitude 9 earthquake versus a magnitude 6 earthquake, How much greater shaking was there in the magnitude 9? How do we calculate that? Same thing, if we have a magnitude 9 earthquake and a magnitude 6 earthquake, how much more energy is released? And remember, whenever we're working with the difference in magnitudes or amplitudes, that's base 10. Energy, we're using base 32 for those calculations. That's all I have for that. That's pretty much what's going to be on the exam. Do any of you have any questions or anything that you want me to go over in front of you as a class? Yeah. The hanging wall versus the foot wall? Sure. Let's see here. Might actually be. Okay, so let's say we have this body of rock. This is the typical denotation for a limestone. So if you ever see this type of unit mapped out, this is a limestone or a calcine. So if we have siltstone and sandstone, and then just sandstone. So let's say we have fault going through that. This is the fault plane. So if you break these into two different portions, if we remove all of this, are we able to walk on this surface? You know what I mean? We removed all of this overlying stuff, then this on top of it. Would we be able to walk up this hill, basically? Yeah. If we removed all of this underlying stuff on this side of the wall, would we be able to walk up this? No. We would have to hang on it. We'd have to rock on it. So the hanging wall is always going to be overriding it. The foot wall is always going to be underneath. The foot wall is going to be the bottom, the hanging wall is going to be the top. Does that make sense? So let's keep talking about this. Let's say we have, we're going to keep the same fault plane, but we're going to move this limestone here. There's a bit of siltstone. It's going to be up here. Okay, so what kind of fault is this? So we have the hanging wall above the foot wall. What kind of fault is this? Thrust fault? It's a thrust fault, right? We have younger rocks right next, older rocks right next to younger rocks. And because we can line these two up, we can see that this has been pushed up because the hanging wall has been pushed up. That means there's a compression force. If this was being pulled apart, this would slump because it's going to follow gravity, going to fall down this fault plane, and then this would be lower. So we would have younger rocks right next to older rocks. So then let's say we erode all of this stuff. So we don't have any more of the sandstone. We wouldn't tell, if this was a blind fault, we couldn't see any of this. All we would see is a lithology change from siltstone to limestone. But because we can see the fault, we can see that these don't line up, so that we know which direction the fault's moving. Any other questions on faults? Okay. Any other questions on anything else? Plate tectonics, calculating half-life.
Today, but I'll talk to you later about it. Huh?
What was that, Levon?
You're gonna review. But
I can't tell if you're talking to me. I guess not. What was your question over here?
Can you talk about the half-life?
Sure, yeah. So half-life is just, let me see if I can find let me pull up that specific lecture that'll help. I think it was in this one. Sure. Okay, so different isotopes of different elements want to eventually, over time, they'll go through radioactive decay. So basically what we know is that at some point, the number of atoms in our sample is there's only going to be half of what we originally had. So if we start with carbon-14 and we're decaying, we break those down over time. And at some point when we take our sample, we see that only half of those atoms of carbon-14 remain. The other half are maybe nitrogen. So that point is the first half-life. That's where we have a 50% ratio between the two. So since we know the half-life of carbon is 5,700 years, and we have a ratio of 50-50, that means we're at one half-life. All we do is if we have take the number of half-lives, multiply it by our half-life age, which is 5,700. So if we only have one half-life, we have that ratio of those atoms, that means the rock is actually aged only 5,700 years. Let's say we have to break it down over time even longer. Now we only have 25 atoms of the original parent material, and we have 75 atoms of nitrogen. That's two half-lives because we broke it down by half, so we have 50-50. We broke that 50 down in half, so now we only have 25 left. So that's two half-lives. Then we would multiply 5,700 pH by 2. And we would get the 11,400. And then same thing and so on. If we break down those 25 atoms again by half, we get 12.5. Now we have 3 half-lives. We multiply it by 3. So does that make sense? Anyone need more clarification on that? Is there a better way of me explaining it? Don't be shy. Okay. Anyone need a refresher on calculating magnitude differences? Magnitude differences? Okay.
Yes, can you go over that?
Yeah, sure. Actually, let me move this.
Is there going to be a formula provided or no?
Will there be a formula provided? That's a good question. Will there be a formula? Probably not. These are pretty simple equations. So like recurrence interval is a pretty easy equation. half-life is just a matter of knowing how many is in each, how many times you divided by 2, basically. So it shouldn't be too bad. Okay, so let's say we have magnitude 8 earthquake. And let's say we want to compare it to a magnitude 4.7. And in this specific question, we're talking about magnitude itself. We're not talking about energy. So what's our base going to be here? 10, very good. All right, so we have magnitude 8, which is 10 to the 8th. This board does not erase well. And divide that by 10 raised to 4.7. Let me know what you get.
Three point three.
3.3, 10 to the 3.3. That's exactly right. So if you divide that, if you multiply that out, what is that number? 10 to the 3.3.
2000.
2000, sounds right. So that means that this earthquake, the magnitude 8, is 2,000 times more shaking, more magnitude, more amplitude than the 4.7. So we're working with a logarithmic scale. So simple rule of thumb, whenever you're dividing exponents with a similar base, you just subtract 8 minus 4.7 is 3.3. So that's a good rule of thumb to use. That'll make the math quicker. So same thing. We're going to use the same example. Magnitude 8, magnitude 4.7. And we want to know the energy released. So what's our base for that one? 32. Very good. So we have 32 raised to the 8th divided by 32 raised to the 4.7. Let me know what you get.
$92,000.
92,680. So 92,680 times more energy is released from this one to that one. So remember, energy, we're dealing with base of 32. Magnitude and amplitude, the amount of shaking, that's where we're dealing with the base 10. Is that good for everyone? Okay. Anything else? I think of anything else that's on the test. Actually, let me pull up the exam. Let me see what's on it. You guys good on rock types? You guys good on, if I gave you a cross section and asked you to tell me which formations are older and younger, would you be able to do that? Okay. How about plate motion from a hot spot? If I showed you a map of Hawaii and told you which ones are younger, which ones are older, would you be able to figure out what direction the plate is moving? Seeing a lot of shaking heads. Okay. This is the worst drawing of Hawaii that you're ever gonna see. Let's see, that's the big guy. And the smaller ones. And they're in a chain. So we know that this is the oldest. And we know that the actual island of Hawaii is the youngest, because that's where we're getting the new volcanism. The rest of these, they're igneous rocks, but they don't have any active volcans. So that means that the hot spot is right below this one here. So that's the youngest. So a good rule of thumb when it comes to establishing plate motion, and you know that this is a linear feature, it's the hot spot is staying still. The only variable that you have is the plate moving over it. What you want to do is just draw an arrow from young to old. That's the direction the plate's going. It's as easy as that. If you imagine the chalkboard moving as I hold this piece of chalk here, if I start here and I move it this way, following that arrow, we're eventually going to get over here. Does that make sense? It's really easy as that. So on the exam, you'll most likely get a series of some feature from a hotspot. It'll tell you how old these are. So you just point from young to old, and that should be the relative plate motion. So if this way is north, which direction is this? West, sort of. Oh, northwest. Yeah, it'll probably be more specific to that. So don't forget your cardinal direction. Okay. All right. If you guys don't have any, oh, was that a question? Oh, it's okay. You got one?
When you're doing slide rescue tasks, how do you evaluate students are best for
That's a good question. So we have isotopes that have a half-life of 5,700 years. How old is the Earth? 4.6 billion years. What is 5,700 years to 4.6 billion years? Nothing. It's a drop in the bucket. So if we have something that has a half-life, say what we studied in zircon, which was those zircon crystals that we found in Australia, the oldest minerals on Earth, they have a half-life of a couple billion years. So that's a better isotope to use when establishing the age of the Earth, because it covers a greater range. If we have a certain number of half-lives with those, then we can tell how old the Earth is. In terms of like carbon, if we have a lot of younger rocks, carbon's great. If we have younger sediments that are newly deposited, carbon's great because it has a young half-life. But in establishing the age of the Earth, you want something with a longer half-life. Does that make sense? Okay.
What was that question?
The question was about which isotopes are best used for establishing the age of the Earth. And the answer is basically, since Earth is 4.6 billion years old, something that has to have a much longer half-life than a couple thousand years. Do you guys on Zoom have any other questions?
No, that was quite helpful.
Okay. All right. Yeah. With Dottie Benioff zones. Pull that up actually. Where is it? There we go. Okay, so Wadati Benioff zones are just basically where we're mapping out earthquakes in cross section. So if we have along each of these graphs, the y-axis is depth into the earth, the x-axis is distance from that trench where we have conversion plate boundaries. Remember, we always get a trench wherever we have convergence because it pulls part of that top overriding plate down. So you get a really deep point. If we map out those earthquakes, we can figure out the angle of subduction. So all a Wadati Benioff zone is, it's a subduction zone that maps out the angle of the subducting plate. So as you can imagine, with that top one, we have a very steep subducting angle that probably indicates that the plate itself is really dense, so it's driving down into the earth. There's a lot of slab pull, there's a lot of convection that's pulling that slab down. At the one on the bottom, which is in Peru, we have a very shallow subduction angle. So that plate that's interacting in Peru is not as dense. It's actually pushing up on the overriding plate a little bit. That's why the Andes get so high, and that's why they're growing into South America. So all a Wadati Benioff zone is, it's just mapping out subduction zones to figure out the angle of the subducting plate. Does that make sense? Yeah.
Could you explain the different earthquakes and volcanism?
The different earthquakes and volcanism you can get from each boundary. Okay. So let's start with where are we gonna go? Trying to find where those are. Okay, so let's start with divergent. Divergent is where they're spreading apart. Divergent, divide. This is where we have tensional stress. And because we're pulling stuff apart, we're going to get a lot of faults along that line of tensional stress as well. Because it's being pulled apart rather than having a bunch of subduction, we're not going to have severe volcanism. We're still going to get igneous activity. We're going to get a lot of stuff, a lot of magma coming up to the surface because we're literally opening up a rift in the Earth's crust. But it's a lot of gentle volcanism. We don't get a lot of earthquakes because, like we said, we get some fracturing, but that's more of the tensional stress. Tensional stress isn't anything compared to thrust stress, which is where we get a lot of the bigger earthquakes. So we get a lot of earthquakes, but they're very they're high frequency, low magnitude, low intensity volcanism, but we get that buildup of magma, which is why we have a ridge at the center rather than just a rift zone and a gap with all that volcanism building up in the center. But as that volcanism cools, as that volcanic material cools, it's going to eventually break apart and then spread across the ocean floor. So divergent boundaries, we get some mild earthquakes, mild volcanism, nothing very serious or particularly hazardous. So let's jump to convergent boundaries. So in this case, we have, on this diagram, we have oceanic continental and oceanic oceanic. So anytime we have divergent plate boundaries where we have subduction zones, that's where we get a lot more volcanism, a lot more violent volcanism, just because as the oceanic plate, since it's dense, it's subducting and pulling into the Earth's mantle. Because it's an oceanic plate, it's full of fluids. Rocks are porous, so they fill up with fluids, seawater, and gases. And as you're melting that rock, you're going to destabilize all of those fluids and gases inside the rock itself. So it's going to start melting the rocks around it. That's why we get those rising magma chambers up through the continental crust, helps to destabilize the continental crust and build up all of those long mountain ranges that we see today. So the Andes is the greatest example of this, where we have an oceanic crustal block subducting beneath the South American plate. So we get a lot of volcanoes in South America, a lot of big volcanoes that have the potential for huge eruptions. This is also where we get the largest earthquakes in the world, the strongest earthquakes. They're always occurring at subduction zones, just because we have so much force and so many stresses applied in the area. You have both plates driving at each other. One plate, as it's subducting, is destabilizing and cracking and fracturing. That's going to produce a lot of strong earthquakes. So convergent boundaries, we get the strongest earthquakes and strongest volcanism. And over to the left, we have oceanic, which is still convergence, but it's two oceanic plates. Since they're both very dense, they're sinking to the bottom. So that's why we have island arcs. We're not building up on top of crustal material, so it's not on the Earth's, it's not on the land surface, but it is going to build up new land through these long island arcs as these volcanoes erupt constantly and build up. They're going to poke up above the seawater. That's what Indonesia is, Malaysia, Philippines. The Aleutian Islands are another one. That's a really good one. We get a lot of volcanism there. But yeah, subduction zones, convergent boundaries, biggest earthquakes, biggest volcanic activity. And then we get to transform boundaries. Where are they? My goodness, I put so much information in here. Transform plate boundaries just means they're sliding past each other. You're going to get some pretty severe earthquakes. Usually, you get a lot more frequent, smaller earthquakes, but you can get magnitude 6 or above. Not the strongest earthquakes on Earth, but still pretty severe and still pretty hazardous. Because they're sliding past each other, you're not going to get a lot of volcanism. There's not enough destabilization on the Earth's crust to bring up any fresh magma. It's not pulling the crust apart to allow for a new open space for magma to come up to the surface. So you're not going to get volcanism at all, really, at these transform boundaries. But you do have to worry about the earthquake risk at these boundaries, transform boundaries where they slide past each other. Because as we know, there are no straight lines in nature. So these models don't accurately reflect what the plate looks like. It's irregular, it's blocky, it's got all these jagged edges that are going to catch onto each other. They'll build up stress. They're going to increase the strain on the rock until it reaches its breaking point. Does that help? Excellent. Anything else? Don't be shy. All righty. Well, if nobody else has any questions, have a great Thursday. Remember, tomorrow, bring a calculator, bring a number 2 pencil because it's going to be on a Scantron sheet. But once you're done with the exam, you're free to go. I'll be in the office for most of the day today, so if you need to drop by, if you have any lingering questions, feel free, Penny 204. So feel free to stop by if you need help. Also, don't forget to submit your Canvas assignments. There's still some stuff on Canvas that haven't been submitted yet, so be sure to get those in too. Those will help you on the exam for studying the exam too.
Hey, Professor.
Yeah, Levon.
Go back into the quizzes to look at the quizzes to study for the exam.
What was that?
Are we able to go back and refer back to the quizzes to study for the exam?
You should be able to. If you go on Canvas, it should allow you to like look at the questions,
All right.
review the questions. If it doesn't, let me know, and I should be able to change that.
All right, sweet. Thank you.
Have a good one.